Check. So live. Okay. Good afternoon. So I hope you had a good lunch. But this mic you may not take, right? Should I turn on this mic also? Okay. Okay. I think uh, without taking much time, what I will, you know, uh, will try to, cover some of the basics of additive manufacturing. So, how many of you know additive manufacturing? Can you just raise your hands? One, two, yeah, except my group. Yeah. Okay. So, which means I can actually go a little bit introductory part. So, those of you know, maybe you have to bear with me for some time. Uh, so before you know uh, I get into the the topic, I would also like to highlight some of the work that we are doing in the AM lab of IIT Harvard. So where you can see a lot of work is actually happening in the area of hybrid additive manufacturing. So I will cover some of the topics in the later class. We will take some of the examples of how what we are doing it. So here we can see that it's a wire arc additive manufacturing, and then we are also adding a post processing, which is enhancing the whatever the printed parts, and then we can see that surface finishing, and then we can actually improvise. These are the some of the walls that are actually printed, and then where you can see building up the the walls without support. So this is a one the video that you can see. This is actually wire laser additive manufacturing, where if you see the typically laser is actually coming in the middle, but the wires actually will be coming from the side when it comes to the DED process. So you might have observed, DED techniques like powder based or other techniques. So where the laser is actually coming from the center, and then the wire or powder will be coming from the side, and then it will actually converge at one point, which is focal point, right? And then you actually build the component. But here it's a slightly opposite, where the wire is actually coming from the middle, and then you have the 6 different lasers, which is actually coming from the side, and then you have the focal point, and then you can actually fuse the material so that you can actually melt the wire. So here you can see this is a typical DED process, which is directed energy deposition, where the powder is actually coming from the side, and then you actually use the center line for passing laser. So this is actually powder based, and then this wire based DED metal 3D printing. Um, so this is another area that we are working on, that where you can actually see how to eliminate some of the conventional technique. Like example, when you want to cast some components, so usually you see that a lot of patterns preparations or molding etc is required. How to actually eliminate all the 4 or 5 different steps that is in the beginning, right? And then you can actually directly go and print the shells using extrusion based technology, right? Then we have different other 3D printing facility, where we actually talk about where we actually work on improving some of the process, and then the materials, and then building up the components and then making a different product, right? So where we actually talk about, like example, if you see that FDM technology, or here you can see that not just single extruder, but you can also see that another head where you can actually use for extrusion process for feeding of clay materials, etc. So this is another facility that we have, where I think extensively used for different biomedical applications, where if you want to actually print implants and then biomedical components, people are actually using extensively that is powder bed fusion technology. So this is a material extrusion, one of the finest you know printer when we talk about printing of a precision parts, right? So technically we can actually print a micron level or micron size components using a material jetting technology, because we actually use a resin for printing the components. So sometime we may need to prepare our own filaments with the different compositions and different materials, or different filler materials, where we actually prepare our own filaments. So here the CMT robot, this is another wire arc additive manufacturing, where we actually use a robot, and then use a conventional welding machine, which is typically for a feeding wire, right? So this is the SLA form laser form 3D printer, where you can actually also, it is similar to the resin based technology, but you can actually speed it up because here we talk about instead of printing a layer by layer, or in printed a point wise, you can actually print entire layer. It is single stretch, right? And then you can actually see the composite 3D printer, where you can actually print a different composite materials, right? So this is just to give you idea that so that you can actually plan some of the projects based on this facility, and for your project, or for next few days. uh, so this is another technology, which is a 4D printing, where you can see that when you actually put inside the hot tub, so where you can actually actuate, and then you can pick the some of the component. So you can also actually do something like different interval you want to actually actuate, like example exoskeleton, right? Where you actually program it at a different intervals, and then you can actually actuate not just a printing, but you can also actually use a different actuators, and then you can actually go for a different programmed components. So I think these are the summer areas that where we actually work on a printing of different components, and then the lab is actually working more than 12 or more than 8 9 PhD students are working on different problems. I think some of them you already met. Some are here. You can meet them over the next few days. Um, so when it comes to the introduction, so I thought since you have come from different background, so it's I think good to understand what exactly the technology, how the technology actually started, how where the technology is actually going forward, right? Why this technology is actually very important, why this much hype for this technology, right? So when we talk about the technologies, right? When we talk about why we needed this technology, and why we need to actually study, and why we should worry about this technology, this workshop I'll be actually talking about how manufacturing is actually shifting from mass production. You might have actually observed say example, if you want to actually fabricate any component, or if you want to actually manufacture any product that today you see, so unless you actually make a big or a bulk or a mass production, so you will not be able to get the break even point early, right? So and how this manufacturing actually shifting producing products in mass production to mass customization, right? So when I say mass customization, so if you see that typical industries, the way they work, right? So they don't, if you go back, 20 years back, so they are very focused with respect to that how industry actually decides. Like example, if you talk about the M4 or M6 screws, right? So if you actually manufacture in a mass, right? So and now it is actually industry set the dimensions. Industry actually set, right, different materials, and industry actually decides, right, how you want actually the components and etc, right? So now if you see that the world actually changing slightly now, right? Now customer actually sets the what exactly you want, right? What exactly is looking for. Right now every industry is having their own way of dealing now the customers, and then different customers you will have in the firm, so you actually can decide, right? And you can actually customize now the components. Like example, if I talk about, like, you have the implant that you want to actually get replaced, right? You will not be required to use some standard components anymore, right? You can actually tell exactly what kind of a size or what kind of a, composition, or what kind of a material that you are actually looking for, right? You will make customization for you, right? So you will make sure that it will actually fit for you. But if you see that still in many field or many manufacturing fields now also, because unavailability of the technologies, right, you have to use some standard components that are actually available, right? And then you have no other option, right, but you have to use it, right? But how to actually come out of that limitation, right? How to actually make a component or make a product that you actually like it, right? That you actually enjoy it, right? That you actually feel that is actually fit for you. Like example, you may wear a helmet, right? You will only buy the helmet which is standard, right? But sometimes that may not actually fit. Sometimes you may have the different sizes, or you are actually in the middle of that, right? You have shoes, right? And then you have the shoe sizes 6, 7, 8, so on, right? Sometimes you need to have actually 7.5, but it is not available, right? Now you need to see, right, how to actually make something like a more customized. You need to see how to, like, how we can actually manufacture such that it will actually fulfill fulfill the criteria, the satisfaction that customer looking for, right? So now why technology is so much is actually adapting, because not just manufacturing alone, right? One is a manufacturing, easy manufacturing. Other things is how complex component can be manufactured. So we always say this: if you can actually design any component, we will be able to manufacture it. So that is the stage that we are at now using this technology, right? So earlier, if your design is so complex, so there is a constraint when it comes to the manufacturing. Like example, I have complex design, right? Now if I want to go for a manufacturing, like if I use a machining, subtractive manufacturing, right? So now I need to worry about what is basically that undercuts that I have, and then how much material that I need to actually remove, and what kind of tools I need, right? And sometimes if you want to actually cut a hard material, right, you need to actually have special tools for that, right? Which means you cannot actually get everything in one place, right? Which is basically, if you talk about a casting, or if you talk about subtractive manufacturing, or if you talk about any traditional manufacturing. And more importantly, that we actually also talk about the lightweight materials, right? So if I actually pick a casting, right, if I want to actually make a structure, right, lightweight, right, I cannot, because it is like you're simply pouring the material, and then you are actually getting the solid structure. Of course you have ways to create the different structures, but and then you need to have dedicated course, dedicated systems or setup wherein you can actually create such a structure. But and then that is only applicable for that component, and then you actually need to remove entirely when you actually go for a next component, right? So and then we have more other factors, multifunctional, right? Like when it comes to that different functionalities of a part, right? To most of these components, when you actually go for conventional, are limited, right? So when it comes to the additive, so whatever you actually design, maybe you will not be able to get a component using one technology, but there are n number of technologies today that are actually available in the market, right? So wherein you can actually use any technology, for that matter you can actually print it. So you will not be able to get a complex structure using a DED or wire arc, but I'm pretty sure you will be able to get in a powder bed fusion technology, right? But and then you have the right technologies that is available, but you need to actually pick the right one, right? So again, we will also actually see fundamentals, and then we will also pick some of the case studies where we will talk about how technology is actually moving forward, how technology is actually going in terms of different fields, right? So as I mentioned, we also like get into a little bit about, we will get into more of a materials and then designs, the defects and then characterizations. So I think the few topics will be covered by Professor Ravi, and then I think characterization, we will also have one more faculty will be actually taking some of the basics of a characterization that will be taught by Professor Anbu Karsi, where she will actually will go through some of the basics of a characterization, right? So as I said, the why this actual technology actually differs in terms of a traditional, right? When we actually see that material flow and then design freedoms, and then we have a toolings, and then we have a customization, and then we have waste, right? When it comes to traditional, right? Like example, if I talk about a subtractive or a formative, right? So anything that we actually talk about a formative, which is say farming, or say forging, or a different way of forming the shape of a component, that we call it as a formative technologies. And then when it comes to the material, the way it flows, right? Only you will be adding the material how much ever it is actually required here, right? And then when it comes to the design freedom, right, where you have the limited when it comes to traditional, but when it comes to additive, you'll have high freedom. As I said, you may not be printing in one place, but you have different other technologies, but and then you will be able to actually get all the designs that you have, right? You have the toolings. When it comes to the most of a traditional manufacturing process, where you need to actually worry about the tooling, right? So you need to have dedicated tools, or special tools for that matter, right? Here you don't need to actually worry about the tools. And then we have the, when it comes to the customization, right? So as I said, if at all I want to actually make a car, so that only you need to have a more of a customized, right? So if you actually go for traditional, you need to actually change many things. But when I actually go for additive, and then highest freedom in terms of changing the tools, and then eliminating the tools, and so on, right? And then when it comes to the waste of the material, which is actually what we need to worry about today, and then tomorrow, and then future, right? How we can actually eliminate waste of a material. Like example, if I talk about a conventional subtractive manufacturing, what we do, we take the bulk of the material, like which we call it as a raw material, or we call it as a subtract, or basically where you actually remove material which is not required. More than 50% of the material has to be cut, or more than 50% of the material actually will go in the form of chips, right? Of course there are ways to recycle, but again that is additional process, right? Which is again you have to bring it back, that material, to the beginning, which is again it will cost you a lot. Now how to we can eliminate the waste in terms of the material? What we try to do here is we try to add the material how much ever it is only required to form a component. So when it comes to the history of additive, right? So this technology is not something the today or yesterday is invented. It's, I think, in fact, just a few days back, the technology actually completed 40 years, right? So this technology is like something invented 40 years back in Japan, where the technology was a more of a prototype, right? So some of you actually heard about rapid prototyping. Like if something you want to achieve quickly, rapid means quickly, right? That's why the name actually started rapid, right? I want to quickly achieve a prototype. Like say example, you are actually building the structure, or if you're actually building the prototype, right? Now you want to actually quickly see the physical part of it, or physical component, and then you want to actually feel it, right? How the component look like, what will be your final output. But it is like maybe scaled down version of it, but it's more of a prototype, right? So that is where the technology actually started, which is stereolithography. So which is where in 94 this technology was actually started shaping it up, and in fact, if you see that today whatever the STL file, which is actually extension of the STL, right? Which is called stereolithography short form, right? So now the technology, they just wanted to have a format. That's why they call it as a STL. Of course, later on they have actually renamed standard language triangles or so on, right? But and then actually the technology actually started from here, and all the STL concept actually started here. But and then people saw that there is much happening when it comes to the technology. As I said, when you have that the technology in place, you can always find you can always apply to different fields, right? Like example, at Texas, University of Texas, so the student actually invented selective laser sintering, which is nothing but SLS, right? So when he actually invented this technology, of course he had used a similar concept, how to create a path plan, and then how to create a CAD file, and then he generated layer by layers. But and then he actually extended to metal, right? Here if you see that, like more of a polymer, and then here he had extended more of a metal, or you can also actually extend for polymer powders or etc., where you can actually sinter it, right? So when you actually sinter the material, right, you can actually form a shapes, right? So that is where he had actually started building up the polymers and then metal components. And then later on FDM, whatever the technology that you actually which is desktop based 3D printing, right, also called FDM technology, right? So this is actually revolution when it comes to the 3D printing. First, when they invented, this is like required a huge amount of maintenance, which is you need to actually have a lot of resins, and then you are selectively curing it, and then making the component. But when it comes to the second case, where we actually talk about a laser, where you need to have a laser, and then you need to have a powders, and then you need to sinter it. But in the third case, which is actually FDM based technology, where you just need the filament, and then extruder, and then actually you fuse it. When you actually fuse it, and then when you actually extrude it, and then you actually form a nicely layers, which is easy when it comes to that building up a technology, or when it comes to using the technologies, right? So that's called later on people have actually started different other names, like example fused filament fabrication, and so many other free form fabrication or desktop printer. Because till today, this when invented and then commercialized by the statuses, till today they only actually have the trademark for FDM technology. But and then question is, why did 30 years, or almost like 25 years it took the technology to emerge? It's all because of patents. So first, all these technologies that I'm talking about were actually patented, and then as you know that, so if you keep on actually paying the patent fees, etc., you can always, you can keep almost like 20 years, right? So somewhere in 2005 or so, right, all this the technologies were actually patent were actually expired, right? So that's why there is a revolution called RepRap revolution that actually happened in somewhere in 2005 or so, where entire community, open, community, that they want to actually build these printers. That is called where you can actually go, and then it's like a Wikipedia, RepRap, right? So you can go there even if you don't know anything. You can simply pick the, what kind of a configuration that you want to actually build, or what kind of a 3D printer that you want to actually build, right? And then you actually, they will have all the details, like what kind of a component that you need, what kind of a, configuration, and what kind of a softwares, etc., you need. And then that is where people started using the technologies, and then they have started building their own technologies, or their own printers, right? So later on, this technology were actually expanded to different other fields, right? So example, as I said, the sources RepRap, where it changed the face of the 3D printer. Today what we are seeing is, right, they now we can actually build a entire 3D printer by yourself. And then since technologists saw lot of improvement, because patents were expired both in terms of polymers, and then both in terms of metals. Now researchers are actually started applying this simple concept of taking the CAD file, and then slicing it, and then getting the physical component out of it, right? Which is like 3D printing, right? So now people started applying, because it is giving a lot of freedoms in terms of printing, in terms of getting a component, right, in terms of getting physical part without much tooling actually required, right? So now a lot of medical field started expanding, because there they need a lot of customized parts, are customized in terms of tissues, or different scaffold printing, etc. That's why there is another field called bioprinting, right? So and then we have other the concrete 3D printing, which is another domain where initially they have started a simple way of extruding the material, and then now they're actually building the houses, right? You might have been aware that in Bangalore the post office are actually built by 3D printing technology. But and then the technology actually started from here. That concept that started from here, using these technologies, and then they have actually expanded, applied this technology for a printing of houses, and then post offices, and in fact the bridges. IIT Hyderabad actually built the bridge, where you can actually use bridges for different places, right? So and now a lot of them are actually using in different fields, where they can actually print the component using additive, and then using hybrid technologies. And then, because as I said, when you actually start a technology, initially you actually focus on a building, right? But and then later on you will see that how to apply into different fields. And then later on, the next step is you will see how to take advantage of these technologies by applying different hybrids, right? So now we are at like where we have the technologies of within additive, and then we have within a conventional manufacturing process. Now we are actually at the stage where we are saying how to take advantage of this multiple manufacturing process, or multiple material combinations, and then we see how we can actually build better in terms of materials, right? So if I talk about the definition, right, if I talk about what is the definition of additive manufacturing, this is actually process like where we actually automate the process of manufacturing of an object or prototypes or tools or entire assembly, right? So when initially technology was actually started, simple parts was the focus, and the later on people actually started printing tools. Now you can actually see that some of them are actually printing assemblies, right? But you need to actually make sure the tolerances and then gaps between these parts, so that you can actually remove if any support structure in the middle of the parts, right? And then more importantly, you are not actually taking anything where you worry about like data issues, right? You're only taking the whatever the data or whatever the components that you want to actually manufacture directly from CAD file, right? Directly you're taking the, imagine you have the software where you actually create a three-dimensional component or three-dimensional, which is CAD file, or you can use a SolidWorks, or you can use a different other way of making a three-dimensional object, which is 3D modeling softwares, right? Whatever you see, right, you will be able to get. That is the basically the crux of this technology, where without using any tools or any specific tools, you will be able to get the object that you saw, right, on a computer, right? It's like a printing something on a 2D. You are actually, if you see that Xerox or all the printers that you see today, right? So that is actually 2D. You are actually printing letters, right? Imagine you're actually adding you add the materials, you go and increase the thickness of the letters, right? Instead of simple ink, and then you actually add the more materials. That is where you actually create a one layer, right? And then you keep on adding the layers or keep on building the letters, right? So that's where you actually build the three-dimensional the structure. So that's why we call it as a layered manufacturing, right? Where you actually build the materials on a layer by layer, right? And then, which is like, if you see that, this is what the CAD file, right? And then you actually slice it, and then you can actually square the edges because you have actually sliced it, right? And then you actually start adding the layers, and then you actually build the component. But and then why, the question is like, why for the first place that actually need to have this slices? Why can't you can actually directly come from year to year, right? So the reason is, so if you see this is actually a solid structure or solid file, which means technically it is a huge file, right? Imagine if it is simple part, simple cube, it will not be that heavy in terms of the data. But imagine if you have bulk materials or bulk components, right, or larger number of components or parts, and then you need to actually slice every time, or you need to actually print. So it is quite challenging, I mean, to understand exactly how much material that where to deposit, right? But instead you take this and then convert into simple file, which is STL, which is nothing but where you have the triangles. When you use the triangles to form the surface. So if you see that initially you may be having CAD file, because we just want outside, which is like surface information, right? So that you can actually have reduce the size of your component, right? So initially you may be having some MBs of size, and then when you actually, because only you take the surface of the information. To take the surface of that information, you can actually use the triangles to represent, because we just need representation, right? Which is like you have the balloon, right? And then you actually put the air, and then you actually form the balloon shapes, right? So that shape is just a simple surface information, right? And then once I have the surface information, and then you have actually reduced entire solid the size, which is like you have the surface information, you actually slice it, right? And then you actually get them, join them together, and then whatever the first bottom layer, when you actually slice it from bottom to the top, right? And then you actually join them, the edges, and then you actually form how much material that you need to actually add it, right? So if I talk about, this is actually the CAD file, right? So if I actually slice it, right, now I'll have the layers of it, each layers. Now if I see from the top, right, so this is edge, this is edge, this is edge, and this is it, and then I'll connect it, right? And then if I see from the top, I will have actually square, and the thickness is what? My layer thickness, right? Which means, think about, if I actually add like this, so I'll be able to get the entire three-dimensional structure. So which means I'll actually form the three-dimensional structures by adding 2D layers. So that is called adding the 2D layers and then to form a 3D structure, right? So that is basically the technology works, where you actually divide it and then see. So the reason, now you have more flexibility, right? What is the flexibility? So when I actually cut it like this, when I actually start adding materials in a 2D, right, so I can have a different materials, I can have different structures, right? Within this bottle I can have n number of materials and n number of geometries, right, n number of flexibilities in just printing this component, which is quite challenging. And then you take any application, sometime it actually you need to have something like this side is a magnetic, and then you need to have this side is a soft material insulator, right? And you don't want to actually add the different joints, right? Now you keep on adding the material, and then you'll be able to getting the magnetic material here, and then you'll be getting the insulator, and then you'll be getting other end materials, right? So such a flexibilities that you will not be you will be able to get using this technology by having this flexibility of adding layer by layer. But and then there is a question, right? What kind of technology that we need to use to have that bonding? Because when you actually add the layers, you also need to make sure that bonding between the layers are important, right? How you will actually ensure bonding between these layers? How you will ensure the penetrate, you have enough penetrating to the previous layer, right? So that is where the technology actually has a challenge, right? And that also will actually give us as a researcher how to actually improve it, right? So that's why aim is actually where you actually divide and then you actually connect them, right? Which is called the strategy, and then we have the, and then you, of course, you may be having different strategies to fill. Like example, I can have a rectilinear, I may have different other path planning. That also actually will affect your the properties of the printed material. So, and then what you are trying to do here is you're actually dividing your complex of structure into simple 2D, and then you are actually trying to fill that path, or trying to fill the gap, so that you can actually form the layers, right? So that is where we actually talk about of course. So when technology actually started, right, a stereolithography, so as I mentioned, so when you have a simple STL file, it is you are only trying to see only the surface information. But say you have something like a color information also, you want to have it, or you want to have a multi-material information, right? Because when it comes to surface information, you will not be able to actually represent color, and then you will not be able to represent the multi-materials. So, but and then the technology limited in terms of a printing of a multi-materials, or printing of a colors, right? So that is when additive manufacturing format actually is taking care of that, where you can also actually add the composition, or you can also add the different colors, then you can also add a different material information, where you can actually get the different information, not just geometric, but also what are the color, and then what are the multi materials. So of course still this format is at a very early stage, because you may be having that format, but if your printer don't have capability of printing a multi material, or if you don't have capability of printing colors, like it's like you have a in the printer black and white printer, but you actually ask the printer color, it can only print black and white. But imagine if your printer has a color printing capabilities, when you actually print color graphs, and then it will actually will give the color print, right? So that is actually the limitation. I think now the technology actually moving in that direction, that how to integrate when it comes to the multi materials, or when it comes to the different composition of the material, how to you can actually add, so that you can actually get the component in a different composition. So as I said, so again, this is like whatever the just now I talked about, like you can basically have the three-dimensional part into different 2D, and then you can actually make it the part into simple in terms of 2D, and then you actually fill it, right? So, and then people actually ask me this question, right? Why this technology is like required now, right? Why this technology is so much in terms of name everywhere, right? So when if you want to actually have any prototype or any product, right, you want to actually speed it up, or you want to actually quickly see the component, or if you want to see if you want to see the part or a prototype within say hours, say within a day or within hours, that some customers want to see that product, right? But you don't have time, right? Now you are basically forced to see that final prototype, which is possibly scaled down version of it, right? But they want to see the physical part of it, so that they can actually feel it, they can actually see that. Like example, something is like a implant, right? Titanium implant, right? So now something is very urgent, and it is very specific to the patient, so you cannot actually use some standard rods or standard implants. Now, can I actually use the technology so that I can actually speed up, right? I don't need to wait for hours, or I don't need to wait for days, right? So this is where the technology is actually taking shape, right? Where you can actually print prototypes or product, and then develop the get the product quickly. So I think, as also mentioned, when you want to actually print something complex structures, right, where you want to see that product which is highly complex, but it is impossible to get that shapes using traditional technologies like casting or machining. So that is where additive manufacturing is actually taking the lead, right? And then more importantly these days, right, when you have multiple applications or multi functionalities, or multiple materials, or and you might have actually seen lot of larger components or larger systems, you have multiple parts or multiple materials. Can we actually take advantage of multi materials, and can we eliminate, instead of 30 parts, can I make it to 5 parts? Think about how many components I'll be able to eliminate, right? How many materials, that how much manufacturing process that I can actually eliminate, right? So you might have actually heard about design for assembly or design for manufacturing, right? So when you actually apply design for a manufacturing, where you actually apply for your additive, right, how many processes you can actually eliminate, right? By eliminating one manufacturing process, you can save a lot of money. Think about if you can actually eliminate 10 components, which means 10 different processes, right? How much time, how much materials and resources that you will be able to actually eliminate, right? So that, think about, like you have thousands of a part to be fabricated, and then you are only printing 100 components, right? How much materials, how much materials, and then in terms of waste, and then etc., you are also saving, right? So, and how you are actually enhancing, right, the parts. And then as I said, many a times that we find when it comes to low volume, right, when it comes to like I need only one component, right, but at the lowest price is I don't have more budget also, right? And it is like volume, low volume, but also personalized, and that only will actually will be applicable for me only, right? Like example, I want something a gadget or something like a car which only I want to see myself, right? I want to have something like very, specific to my, you know, specification or my, demands, right? So will I be able to achieve it, right? Right, and more importantly, how much freedom that you have in terms of making such a, component or product, right? So, and then, as I said, at the end of the day, that you will see material reduces and the waste, and then when you actually compare with the traditional methods, right? So that is when we actually talk about, different materials, etc. So I think we have talked about some of the aspects. When it comes to that, why one is, how technology is actually, moving. Another thing is why, why we need to actually see, like why we need to use it, right? One is like, although there is a technology, but you may not have enough resources, or you may not have enough, in terms of usage, or you don't have a basically facility, or you don't have the opportunity to use it, right? But here we have actually come long way now, right? Where we have seen the technology in early stage in terms of development, and then we have seen how the technology were actually using it in different applications. Now we are actually seeing how the data is available, right? How what exactly you are looking for, you will actually will get now, right? So example, now wide availability of, CAD softwares earlier. So even if you want to actually use a printer, any polymer printer, so you need to actually have the software for a modeling, or creating a three-dimensional. Maybe some of you might have actually, for 20 years back or 15 years back, we'll be having limited in sort of a CATIA, or Unigraphics, or so on, and most of them are actually paid versions, right? Now you don't need to actually worry about it, right? Because you have n number of options now, right? You can just go and Google it, that I want to create some, three-dimensional CAD file, and then you will find n number of websites where you're all free now, right? So you don't need to worry about, right, creating a three-dimensional file, right? And then lot of improvement in terms of automation, and then component technologies, and then more importantly, so when, 10 years back, so if at all I want to actually use a, mild steel, or if I want to use a titanium, right, for a printing implants, right? So I need to actually, set up, or I need to actually work on a printing parameters. I need to work on a, how to build a library. Now if you actually type it, right, that is example titanium, and then you will have every information, what kind of, composition, what kind of a material that you need to use it, and then what kind of, properties that you will achieve if you actually use this process parameter. Now people are actually build enough, in terms of the library, where you can actually use readily, and then you can actually print it. And then more importantly, any technologies for that matter, if you see that investments that from industries and then government will play a major role, right? In 2012, US government actually announced this, technology will going to take a, disruptive in manufacturing in the industry. It says in 2012, it was announced by, then President of United States, Barack Obama. So then after that, you will find everywhere, every different countries started actually setting up a center of excellence in additive manufacturing, right? You might have seen, India also, we have a couple of, national center for additive manufacturing, and then many other, and then US, they have multiple center of excellences, or so on, where, government itself is actually investing, because they are seeing that this technology will actually will take it forward, right? Technology will actually, we actually will help us making the components, or easiest manufacturing industry, right? Now India also actually invested a lot of money, in terms of setting up, different infrastructures and different IITs, and then IISc, and then NIT, and then there are dedicated, centers where you will find a good number of metal 3D printers now, right? Now I think, second most important, right? So this is actually where it actually changed the face of technology, for that matter any technology, right? So that's why I tell every time, so if you have idea, you simply actually patent it, it will actually stay with you for longer time, right? So because it took another 20 to 30 years, for technology to emerge, and if that patent were not there, but I mean 30 years back itself, you have been in the market now, but it was there in the market, but and then there are a lot of patents were actually valid, and then they need to only actually manufacture some of the machines. Now almost all the patents were actually expired, in terms of now you can actually build your own printers, whatever that metal 3D printers or polymers or that I have discussed. And of course there are cases like where they still have the trademark, example FDM, SLS. So these are the actual trademarks where actually they will still have the trademarks with the company, so they will actually operate it. But and then you can actually use the technology, and then you can actually build by yourself. And then more importantly, there is a lot of momentum, and then people are actually working, they're actually generating a lot of data, then they're actually printing using the technology for a different in different fields. And then there is a confidence that yes, this technology is actually usable, and then I can actually invest. Why industry actually invest? Well, they will only invest when they feel there is a confidence, and then they will when they feel there is a future for this technology, right? So and then of course, as I mentioned, anything that you actually thought about it, you'll be able to print it. So that is the creativity, or that is the design flexibility that you will have. Say something you thought, in a dream something, okay, I saw something is like, picture is coming something like this, now I would like to draw it, and then you will have you can actually see that component. So that is the freedom that you have when it comes to the technology, right? So think about this, you can see this cup, simple cup, right? So where you have the series of complicate in terms of, in it example, can I actually machine this component, how difficult machining of this component, right? And there is actually the undercuts here, right? You may be having a simple block when it comes to starting of it, right? So can I actually access this area, can I access this area? But yes, it is possible if I can actually tilt it. But there is a question, there is a small or thin valves, right? How I'll be able to actually retain it without when I actually go for a machining, right? When I actually go for a casting, what is the status of this guy? Can I actually separately cast it two, and then can I join them together? And what will be the status of this joint? Will I have another process which is joining process, right? So can I actually print entire component in single go? If you ask me, yes. But and then question is how far when it comes to the layers, bonding, right? How far, how good when it comes to that structure surface finishing, right? How good when it comes to that holding of this grips or the holder, right? So how in terms of the component as a whole, right? So these are the questions that we actually ask when it comes to the printing of any component, right? So if you see that technology point of view, right, there are common when it comes to traditional, right? Example, you might have actually seen about CNC machining, right? So if you see that typical CNC machine, what they do, so you actually use a different CAD software, so where you actually design, and then you actually try to see the you create the path plan for your component, and then you actually machine that, right? Here we actually use the slicing, and then we actually slice the data without much tools, or without any using special tools, you will be able to achieve the final the component, right? System is actually tightly integrated when you actually compare with conventional or traditional path planning. So I think we'll stop it here, but maybe we'll take few questions. Yeah. Any questions? We have 5 minutes and then we'll take few questions. Any questions? So if there are no questions, I'll take another 5 minutes. What do you suggest me? Yeah.
It is additive manufacturing is of low volume.
Right.
Then how can we design according to us and with freedom?
So when I say low volume, I think there are two things. One is how many number of components that you want to actually fabricate. Say, so this is actually the component that you want to actually fabricate. Now, if I want to go for a traditional casting, right? So I need to actually have the mold, right? Means I need to actually prepare the tools for a molding, which means I need to actually go for a machining, which is like where we actually get the mold sizes, right? And then you actually use a blow molding to make it this component, right? I mean, it's a typical manufacturing process for making a bottle, which is blow molding, right? For that, you need to actually have the, you know, like exactly the shape that you need to actually have the mirror of it, right? And then you actually blow it, the polymer, and then you actually get the shape. Now, suddenly, if I want to actually change the shape of this, right? So, after preparing, now I felt that the size I got a component is not a good for me. Now I want to actually go for a bigger, right? Which means now I have to again change entire, design, mold design, and then I need to actually again go for a conventional manufacturing process to prepare the tools. Which means, so if at all I want to actually imagine 2 3 components, again I need to actually keep on changing, which is called low volume, right? Sometimes you have the batch production, right? Only say example you want to have 10 components of 10 different parts, right? So and then you need to actually prepare entire molds, which is like sometimes not feasible. Sometimes the part cost is like example 10 rupees, but even for preparing 10 rupees component, the mold itself you need to actually invest high, right? So that investment that you actually put on a, like example, preparing the molds and the tools will be at least 10 times. But is it really worth it, right? So and after you invest that much money for making molds and then tools, etc., and then you cannot actually use it for other components because shapes are different. But what I'm saying here is, so you no need to actually worry about preparing the molds here. Whatever the size that you are actually looking for, you can directly print it, right? Without using a molds or without using a tools or without preparing a tools, right? If you want to change it, the dimension, and then you say example, initially maybe having this size and then you increase the size. You just change in a CAD file and then convert into STL file and then print it different size of a component, which means I have a freedom even if we are actually going at the low volume, right? I don't need to actually only worry about every time the cost to the component, right? Say example, if I want to make a components of like 10 rupees, right, I can as well make it a 10 rupees component only, right? Of course there is initial investment when it comes to the printing, but even after print, even in conventional also you'll have to have investments, high investment when it comes to machining machines, and then you have the shop floors and then many other this thing. But that initial investment is everywhere in the when it comes to that investment part. But when it comes to the flexibility, once you change it, how much flexibility that you will have when you actually change the sizes and then dimensions and then materials, etc. So that you will not have when it comes to the conventional. So that is where we talk about when it comes to low volume, it is easy when it comes to additive, because you have all the freedoms to change the shapes or the dimensions, and then you quickly achieve how much our time it takes, right? But of course, time is other this thing that how quickly you'll be able to achieve. Of course, you see that in conventional also, like example, if you go for a fitting and then you go for this thing, we will be able to achieve a little early, but suddenly change the dimensions, you will not be able to achieve. Yeah, I hope I answered you.
So when we call about additive manufacturing, it is here by laser. So when the final product is manufactured,
Mhm.
the surface is not smooth.
Yeah.
So for finishing we go for the conventional machine.
So you are asking me, can we go for conventional machining? Yes, that's we call it hybrid. So what happens? Like example, imagine this is a 3D printed component, right? You can see the steps here. Of course, these steps they gave for a different purpose, right? So here, when you actually see these steps, now you want to actually eliminate the steps. This is called basically you have the different layers, right? So what you do is actually apply the machining and then remove the material, like which is small amount of material can be removed. That is fine. That is called post processing. That is now the hybrid technology. Yeah, you can use it actually. But of course, when you actually go for post processing, how much what kind of a tool and then what kind of a fluid you're actually using while machining, and that is also important, right? Sometime it will also will actually affect your material, right? How early you're also actually flood the coolant is actually coming in contact with the materials, right? How what is the solidification rate? So that also actually will play the role. Yeah, but yeah, lot of things are actually happening in that area where you can actually go for a machining of after printing. Any other questions?
When we fuse between two layers,
Mhm.
does it change the material properties?
It depends, right? So imagine this is the first layer, that which is like a fused or you may think about like laser based technology, right? So when you add it and then you actually spread the powder, or you add the fresh layer, which is like when you actually talk about a DED, so the powder is actually coming and then you are actually fusing it. When you talk about the powder bed fusion, you are actually spreading the powder and then you are actually fusing it, right? So how much the depth, how much penetration happening to the previous layer will play a major role. More the penetration, which means you are actually remelting it, right? When you actually remelt, your properties can be enhanced, right? But if there is a less penetration, your properties may not be enhancing, but you may be actually saving some energy, right, by not penetrating. But you may be also actually compromising how that bonding between the layers. The bonding between the layers are also important equally, because if you actually print the layers, if you don't have proper bonding between the layers, it will peel off it up, right? So to overcome, you need to actually give enough or sufficient amount of an laser power, so that it actually penetrates enough to the previous built layer or first layer, so that you can actually have bonds between the few layers. So then only you will, of course, properties definitely will vary. That's where many times 3D printed component properties may not be uniform across in the component. You may have different, but we have to see how close we can actually achieve properties in all direction. Like example, when you actually add them layer by layer, so you are actually every time you're actually fusing it, and then actually it is affecting a previous layer, and then you are actually penetrating. But this may not be when it comes to the layer overlap, right? If when you actually see from the top, so overlap is actually happening between the layers, right? So there is no penetration, but there is overlap. So that will have different issues, or that will have different remelting, right? So that's why the properties in x and y, and then properties in z direction will be different, because the reason being z actually will vary how close or how much it is actually penetrating to previous layer, and then x and y, how much you are actually overlapping between the layers will play. If you have less overlap, and then you have weak bonding, and then you have less penetration, you will have weak in terms of overlap between, sorry, in terms of bonding between the two layers, right? Of course it will affect. So but you need to see how optimally you can actually select the right process parameter, so that you will actually achieve both bonding, and then as well as between the layers.
Mechanical component like then go through
They will go through,
heating
yeah, heat treatment, right? So example, what happens, so when you actually build a component, right? So think about, you have a powder based technology, right? So you, although you may be actually melting layer by layer, right? But still some amount of porosity might have actually created, or some amount of some impurities are actually trapped inside your melt pool, because you are actually creating the melt pool, huh? When you actually create a melt pool, it is actually you are forming a liquid pool, right? When you actually form a liquid pool, if you don't actually protect the pool, and then sometime penetration, that impurities can actually penetrate, right? So it will also will actually cause some amount of porosity, right? If you want to actually remove the porosity, or if you want to actually remove the impurities, so you need to actually go for a heat treatment, so that you can actually enhance, so that you can actually, if any unmelt or partially melted material actually liquefied, or it will actually go and then occupy the wherever the space available, right? That's why you, of course there are ways in which you can actually go for a post treatment, but mainly they go for enhancing the properties of a 3D printed parts. Mainly some of the issues while printing might have actually generated like impurities and then defects, small defects. So that can be sometime, may not be 100% you can actually eliminate, but you can actually improvise, or you can actually make a better in terms of a component.
treatment won't
It will affect,
affect the layer connection.
it will enhance, it will be better, because say you have partially the materials melted, when you actually put inside the furnace, so when you actually increase the heat, the bonding will be better. So it will actually will go, and slightly it will melt it off, and then bonding will happen, because what happens if you if you actually heat the material, when you actually go for higher the temperature, more the material melting will start, and then you'll have better bonding. Of course overheating is also will actually spill over it, but optimally you can actually enhance when you actually go for a heat treatment. What is the tessellation? So that is a good question. So think about, um, so this is a solid structure, right? So imagine you have actually created a CAD file of this. Now this is technically heavy. Our file size is too, you know, I mean, maybe if it is just say 15 by say 100 by 70, so this component seems okay, right? This is actually doable. But you think about, like, I have something like component like this, or component like bigger. Think about how much the size of the component. So handling itself, you need a better computer. Handling itself, you need a better software, right? So and then processing itself is another headache, like, printing, right? Printing, for you, like example, I have a printer, right? I cannot actually load entire data to print the component, but and also machine will not understand, right? Example, if you see all your CNC machines cannot understand even the file size. You may be having components, bigger components, you will be actually machining it, so you will not have any that big data in the data is actually feeding into a CNC machine. So what you are actually feeding, you need actually G code, geometric code, right? So what is the geometric code? X and Y. So to get X and Y, so what is the easy way? Make it a smaller, and then and that's why you make it, triangles, and then you, after triangles, you actually further divide it, because at the end of the day, right? So if I want to move from year to year, machine only will understand G code, nothing else, right? That's the machine language, right? Whatever the stepper motor, whatever the motor that we talk about, right? So if you say X is this much, it will move X. Y is this much, it will move in Y direction. If Z means, it will move like this. I just need that coordinate information. What is my next step? For that, I just need information. For that, better, I will just give as much as smaller information, as much as smaller data, so that it is easy to process. If I give a bulk of the CAD file, technically I should give that entire CAD file to machine, which is not possible, right? So at the end of the day, you need to actually make it a smaller sizes, or where machine can understand, right? So that's why you actually need that tessellation format. Otherwise, I mean, some companies actually did it. Example, HP have their own software, so they don't actually use STL file, so they use their own file. But still, so they have series of steps where they take the CAD file, and then they actually convert it to HP file format. Again, it is a similar principle, that at the end of the day, machine can only understand geometric information, how much Z has to move, and then how much, at the end of the day, mechanical system, all the stepper motors or DC motors simply works on whatever the step size that you give, actually only work on it, right? Only that much. You are, for what you are actually using this, all this, you are only using for a movement, right? Your head is different. Head is what you are actually using for adding the material or machining it. Like one case, you are actually machining it, other case you are actually adding it. That is a two opposite when it comes to material. One is you are adding, other is removing. But in both places, you are actually using a head, or both places you are using X and Y, Z, right? One, you are actually coming from bottom to top, other cases maybe top to bottom. You are actually, we are removing, and then you are actually adding the material when it comes to the additive. So that's all the two different when it comes to, but that principle or philosophy is same, that where you are actually giving instructions to the machine, how much X, how much Y, how much Z you are supposed to move, and how accurately, or when it comes to that, like example circular, how two motors together should run, or together should actually move forward. So that is what why we need a simplified version of it. It's like simplifying your data. It's a simple language. Like once you simplify the data, then only it is easy for you. Otherwise, it is difficult. You're trying to simplify. That's all. Because I think HP, and then there is another two more companies. They don't actually use STL, so they use their own format. But it is okay. I think as long as you are simplifying the data, and then at the end of the day, you are only using X and Y, and then Z, and then different. And sometimes some of the technologies don't even use it. They use a galvanometer and then just work around. Yeah. If I have. Uh-huh. No, no, this is polymer and metal. Okay. So, so what we, I think sometime when you have two, extreme material, right? Bonding between these two materials are quite challenging. So instead, what we, I think many, researchers actually try to do. So you have the polymer, right, and then you actually add a metal powder while actually you prepare a component, and then you see that how, what is the composition that you are actually looking for it, right? Say example, if you are looking for a metal, composite say 90%, and then you actually put the 90% of the metal powder and then 10% of polymer. That is one way of it, doing it. So other ways, so you simply insert your metal component and then add the layer materials on the top of it, right? Which means, so example, imagine this is a bed. Initially you actually add a few layers with the polymer, and then you actually insert your metal component, right? And then you create enough, space for inserting a metal component, all right, and then you actually add the material on the top. So there are different techniques, like how to place them and then how to hook them, like what is the, pattern that you should follow, and then you actually add the material. Then you can actually add the materials layer by layer. So that is called integrated, system, they actually call it. So when you actually integrate with the polymer, so and then it will actually will create a bonding between the, because since again, you may not have, better bonding sometime, right? If you don't actually place it in the right place, when you actually place the component. But people have actually tried that, placing it, because when you actually add a metal and then adding another polymer, which means you need to actually make sure what is the height of your polymer material and then metal component that you have actually inserted. So and then it has to, stick to each other, right? So that how much, sticking, and then what is the basically the bonding between that sticking material and then your metal is also important, and what is the basically that, the area that you are also filling is also important. I mean, I think it is quite, easy when you actually go for printing of, make, say example, some components anywhere 50 to, 100 sizes. But anything smaller is little challenging, but anything little, you go for a bigger, because it, when you actually put the any inserts, and then you need to actually go for more areas to print, so then you can give the better bonding. Yeah, I hope I have answered. I think you can show our, the, that Syed did it, no, that polymer and then nitinol. So you can. Hmm. How much size? Okay. Okay. So the this clamp is polymer. Okay, and then the rod is metal. Uh-huh. Uh-huh. Hmm. Okay. Yeah, I think one. I think the best way is, I think you can actually go for, preparing, initially the, the structure assembly kind of a structure, where you actually insert it, and then with having a support structure of assembly, and then you actually print on the top, and then you can create it. Just, I think, explore. I think you, Akshay will take you around, so see if you can actually put that, and maybe FDM is should be okay. So I think, what is the break time? Oh, we are exceeding. Okay. Okay. Thank you all. What is the next session? Who is it giving? Okay. Okay. Thank you all. If you have any questions, I think, but is it a tea after the tea or? Okay. We'll have a tea and then after that we can join again.